Hello all, and welcome to the first of what will hopefully be many VHDL tutorial videos. Today we're going to start with a button debounce, and a button debounce that is not as straightforward as a lot of others. I'm aiming to complete a button debounce that is fairly versatile in the sense that you can use buttons and or switches with it. You can have it output a single clock cycle pulse, or you can have it just show the state of the button or switch after a debounce period. So let's get started, and I will apologize in advance that my mechanical keyboard may make a bit of noise in the video. So I've taken the liberty of filling out the libraries, and in this case the only library you'll need apart from the standard set is numeric_standard. So we'll begin with the entity button debounce. And we're going to put in some generics into this. So the first generic I'm going to do, I'm going to call it pulse. And the idea of pulse is this is going to be a Boolean that basically says if you want a pulse output, so I press a button and I get a single clock cycle pulse, or if it's false, what you get is you get the debounce period and then whatever state the switch or button is. So for this we're going to call it Boolean. So I'm going to default that to true, purely because I am a big fan of single clock cycle pulses from buttons. I feel it makes it a lot easier. The next one we're going to do is simply one that checks if we've got an active low or active high. In the case of a switch, what this will do is this will basically invert the switch, so if it's down it'll appear as up and vice versa. For a button, and that's what this is more targeted at, is a button, is that it will give us a proper value depending on the button is an active low, so 0 when pressed, or active high, or 1 when pressed. Now the particular board that I'm using at the moment is a DE0 from Altera. And they have active low buttons on them, so I'm going to default that to active low. Finally, we're going to put a delay in there. I've just realized that I forgot to put a Boolean there, so I'll just update that. And like I was saying, the last one is a delay, and this is simply going to allow us to define our delay period. And I'm just going to put that as an integer. I'm not going to define a range for that. And since the DE0 has a 50 megahertz clock, I'm going to put this as 50,000 because 50,000 clock cycles is 1 millisecond. And I will be doing a process that the whole period is not going to be 1 millisecond, it's going to be 10 milliseconds in total, but we will get to that. So that is our generics. Next we move to the port. And we begin with my favorite and most important thing, the clock. In standard logic, single bit, we will put a reset in this. Again, single bit standard logic, and I'm just going to leave a note to myself that we're going to make this active low. The button input in standard logic as well. And finally the output, which I'll just call debounce. And that's standard logic. And that should be our entity, so I can end the entity. Excellent. So we can start our architecture now. Architecture arc of button debounce is, and I'm going to start with my signal sample. Now the idea of my button debounce, the way that I'm approaching this button debounce, is to define 10 bits. So I'll do that now. 9 down to 0. And what we're going to do is, when we're polling the value, when we're looking for the button's state, and we are waiting out 10 milliseconds. Every millisecond, I'm going to put the state of the button into the lowest bit of this vector, and at the same time shift the rest of the vector left by 1. And the idea is if I keep polling this information, keep going to the lowest bit and going, what's the button at now? What's the button at now? What's the button at now? I will only ever get all 1s or all 0s when the button has stopped bouncing. So a bounce in the system, a bounce in the button will appear as some combination of 1s or 0s. And I'll only let this component output a value when it's all 1s or all 0s and nothing else. Now with that in mind, because I don't want any false outputs at the very start, I'm actually going to give this a default value that is a mixture of 1s and 0s. And that is just because when we start this, the component will have a value that it's not going to output anything, and then it will settle to one state or another. The next signal that I want is what I'm going to call sample pulse. And sample pulse is just going to be a pulse that tells us to actually sample the button. So that 1 millisecond, every millisecond where we take the value of the button and put it into our sample signal. And I'm going to give that a default value of 0. They should be the only two signals that I need, so we can begin. We're going to begin process clock. I'm just going to move that down a bit. And we'll call this, well, this one's going to be our clock divider. And let's begin. Oh, actually let's not begin just yet. I will put a variable in there. And I'll put a variable called count, which is going to be an integer. And this will just be the variable that I use to keep incrementing until I reach that delay that I defined in the generic. And this will just default 0. Very important that you put this one in. I've found that you can have issues if you don't include this, its default value, because the system can, the design can get stuck in a state where you need to reset it to actually get count back to a value that's below delay. I'm not entirely sure why this has happened. Either way, it's good practice to do this. So get in the habit of defining default values. In the end, you'll find that it allows you to avoid having weird errors in your design that can be quite hard to debug. So we'll begin it. Clock dash event and clock equals 1. Then we'll put our reset in there. If reset equals 0, like I said, an active low reset. And if the reset goes to 0, I want to reset my count. And always remember, when you're doing a variable, you don't do an arrow like you're pointing, you do colon equals. And sample pulse, oops, missed the pulse, defaults to 0. Else. Now we do our counter. If count is less than delay, then count is just going to increment, and we make sure that sample pulse is still a 0. Else count resets, and sample pulse goes to a 1. And what this will do is this will ensure that on that one clock cycle where we've actually exceeded this value, so count has finally got, actually not exceeded, it equals this value, what will happen is that one clock cycle we'll have a sample pulse of 1. And what we're going to do is in the next process, we're going to take that single clock cycle of sample pulse being 1 and use it to input the button into our sample. So we will close this process, so end if, and you'll find that I use an indentation guide just to keep track of my if, else ifs. I find this to be a very useful tool from Quartus, and if no one knows where to find it, you just go to view and it's just right there. I don't remember what the shortcut is off the top of my head, but a useful tool. We end if for the clock, and we end the process. So this is just going to act as an in-component clock divider. Next one is going to be our sampling process. And I don't need any variables for this one, so I will start with, as always, my clock dash event and clock equals 1. You're allowed to use the rising edge function for these. I'm just in the habit of writing clock event and clock equals 1. We put our reset in. And then if we're resetting, we want to give sample its default state. Now, we need to be clever about this, because for sample, which is constantly polling information from the button or switch, we don't want to force this to default to either a 0 or 1. We want it to default to the button state when the system is reset. This is the most stable way to reset this sample signal, and we're going to do that by using the others function in this context, and I'm going to write it to the input, which means if I do this, what it will do is it will write every bit of sample to this bit, and this bit will be whatever the button equals at that time. So this is the same function that I personally use to say write an entire standard logic vector regardless of its size to 0 to effectively reset it. And in this context, I'm just going to use it with the button as an input. So that's all we need there. The next thing is to put the else, and we will do if sample pulse, which is there my single clock cycle sample pulse. Then sample 9 down to 1. Sample 8 down to 0. So what this is this is my left shift. Is that I am taking the top 9 bits of this, I'm taking the bottom 8 bits of this, 9 bits, bottom 9 bits, and writing it to the top 9 bits. Very simple way to do just a left shift of a vector. And I'm also going to look at the lowest bit, which is 0, and pass input to that. And that's all you need for the sampling. And while I'm thinking of it, I've been asked before about, and have used myself, I've been asked about passing in clock dividers into the components. So just having a slower clock come in on your clock input. Now, I'm not personally a fan of this because I think it restricts your ability to have a versatile button debounce, and most importantly, if my system is running at 50 meg but this component is running at 1 kilohertz, this sample pulse will still be a 1 clock cycle in this component, but on the top levels end, which is running at 50 megahertz, this sample pulse is going to last 50,000 clock cycles, and that is the same with the button debounce that I want to output for a single clock cycle for the top level to interpret. It's just better to work at the native clock speed and then divide where needed. And that means that with this, I only divide where I need it, which is in this case for the sample pulse. But when I'm going to pass my output would be a single clock cycle at the native clock speed, which is 50 megahertz. So this is why I opt to include my clock divider in the component. Anyway, moving on. The next process, and the main process, is going to be my button debouncing. And I'm going to give this one a variable, which I'll call flag, very generically. And again, a default value, which will be 0. And we begin. So, if clock dash event and clock equals 1, then I'm going to space this out a little wider so it's easy to interpret. If reset equals 0, whoops, then debounce equals 0. So this one, I'm opting to write this to either a 1 or a 0 simply because I find it's a bit safer to do it that way. I could just not write this to anything, but there's a chance that even if I reset these in these other processes, Debounce will retain its state and continue to output a state even if it's not the one you want at the reset. So I'm going to write the reset condition for Debounce as 0 as the default. Okay, so we've got our reset. That's all you need for the reset. Now let's start with if active low. Oops. So now we're looking at one of the Booleans, and basically me just saying if active low is, this is the true condition. If it's active low, it's true. I am then going to start the if pulse. So now we're looking at if pulse is true. So this first one, we're looking at, we have an active low switch or button, and we're looking to pulse the output. So we need to look at the sample signal. And we need to see if the sample signal is where it should be. So if sample, again, we're looking at active low. So we're looking for zeros. And 10 zeros to be precise. Then we've got, if we've got this sample equals all zeros, then theoretically we've got a switch or button that's not bouncing anymore and is at 0. We want to check the flag, that variable I defined. The reason I've defined that flag is to control the pulse, to basically force the system to only allow the pulse output. So we're going to check if it's 0, if it's in its ready state. So the flag's in its ready state. We're going to write debounce as a 1. So we have an output. And we're going to write flag as a 1. Now I'm going to put an else for this and write debounce is a 0. So what you'll see this does here is that we check for our flag being ready, and if it's ready, we allow debounce to be written as a 1. I also immediately write flag as 1. So this all occurs in the same clock cycle, which means that the next clock cycle this comes around and checks this flag has already been written to a 1, which means that we're in this statement now. So debounce on the very next clock cycle goes to a 0. Means that we have a single clock cycle that debounce is a 1. So we end this statement, and then we go else here. So else of this statement. And here, I'm going to write a debounce of 0 just as a precaution. But most importantly, this is where I'm going to write flag back as a 0. And what that means is that the flag cannot be put back into its ready state until the button or switch leaves this condition that triggered it in the first place. That basically means that it's a single trigger event, is that I can only press this button once. If I'm holding this button or holding the switch in one position, this flag will never reset. It's going to wait for the next one. And on your top level code, if you're working with synchronous designs, this can really help with not needing to try and call buttons or switches with rising edge functions, which is absolutely my preferred method. So we'll end this statement. And basically what this is now is this here is our active low pulse out. So let's now look at if we didn't want to pulse. We wanted it to hold its value. Then again, we just check the sample because we have to check the sample. And I'm just going to save myself time and copy paste that. I should have done that. I missed. One too many. Then debounce is 1. We have an output. Else if sample equals all ones. 1, 2, 3, 4, 5. Then debounce equals 0. And the reason I've explicitly called the sample equals all ones here instead of just writing an else is that I don't want this value in this mode to go back to 0 while it's bouncing. So if you think of this like, this is going to be more commonly used for a switch, for example, is that I have my switch in the down position, which if I'm active low, then it's a 1 output here. And if I slide my switch up, I don't want that value to update until this is done debouncing. So I'm going to explicitly say this or this exactly, and everything in between is not going to affect it. And that's all we need for that. And this is our active low. What we'll call it is we'll call it constant out. Cool. So now we've done that, and we can end this statement for the pulse. And now for this indentation, we're looking at the active low again. So if I put an else there, now we're looking at active high systems. We do the pulse again. This process gets a little large, but that's all right. And just as previously, we look at the sample, but we're in an active high system now. So now we're looking for all ones. And what will happen is it's actually going to operate exactly the same as the previous statement, except that we're only looking for the ones this time, not the zeros. So if the sample's all ones, then we want an output. Oops, no, I'm getting ahead of myself there, sorry. We need to check the flag. So we are doing our active high pulse out. So in this case, I need to do the flag. So I need to check the flag here and check that it's in its ready state. And if it's in its ready state, then as previously, the debounce is allowed to become a 1. The flag has to become a 1. And if the flag is now not at 0, we want these two to, nope, I didn't want a flag. We want debounce to become a 0. And we can end that statement there. Else flag becomes a 0, so it becomes its ready state. And debounce becomes a 0, so it's not outputting anything. And we can then end that statement. Yes, we can. Now we look at if we want the constant output. And again, we're in a active high system this time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then active high constant out. Debounce equals 1. Else debounce is a 0. And I have again forgotten something. It should be else if sample equals 9, 10. And we end that statement. We can end this. We can pretty much close up the entire process now. I know that each of these indentations is caused by an if, so I can just very simply, without even looking at it, just close each one of them until I get to the end and close the process. And the final stage is to end the architecture. And with that, I'll save the file and we'll just run the analysis on it to make sure that I'm not giving you anything that's incorrect. Assuming that I've done this code previously, it should work out okay. Which it has, so there we go. So in conclusion, what we've done here is we've done a button debounce that can be applied to a variety of situations and buttons or switches, and can hopefully service most of the needs that you would have for a button or switch in your designs. I will post this code online. Please find the link included below if you'd like to use the code. I'm perfectly happy with you using the code. That's the exact reason why I'm doing this video. So I hope this video has helped. I hope this video has helped you all, and please keep an eye out for videos in the future.